Okay, for kind of a tutorial, let's look at this exercise. Is x dx square root of 9 plus x squared. So what do you think we must do then? First of all, before you integrate, you must have a kind of a glossary, I don't know the glossary or whatever, or dictionary of integrals. First of all, must be able to say this is a power rule form of integral or a linear form of integral or a trigonometric and or exponential. Is that right? That's what you must think first of all. And when it's logarithm, when you think it's logarithm, normally we said in our discussion that the logarithms of differential for the derivatives of logarithm functions, they always turn up to be ratios, isn't it? But now, is this a ratio which can be of lead to linear form of integral? Do you think so? No, no, because when you've got a linear function, when you're going to have an integral which is a linear function, you must first of all think of a derivative of that function. This derivative of this function is always saying we have f prime there. I mean, that discussion is known by now. If it's a derivative, you give f prime over f of x. Is that right? Now, but now the f, this, to say this, the integral of this is that, we must first check the whole denominator, whether it differentiates to that. But now, a denominator here, what kind of a function is in denominator? You have forgotten that square root of 2, square root of x is equal to a power half. You have forgotten that. If you have forgotten those things, then these problems are not going to be able to do them. So this is actually a power function. Now, then that's why I'm saying that these ideas must be there when you deal with this problem. Now, we have to think about the power function, standard integral for a power function, or let's say standard derivative for a power function. Let's take a power function and differentiate it. Why am I going back to differentiation? Because I know from previous discussion, what is under the integral sign is a derivative, isn't it? So I want to see whether this function is going to take me to a power function. So first of all, let me look at the standard form of a derivative of a power function. Then say derivative. Then this is going to be equals to n f at x to the power n minus 1. Is that complete? Is that complete? Must apply by the derivative of the argument. So that's that. So what am I saying there? I'm saying what must appear integral sign must have this form if it is to be integrated back to a power function. So then, since we've got this kind of equivalence, then it would be nice to write this in that form and see whether we can see some kind of relationship. So we can say 9 plus x to the power half, no, x to the power 2, all this to the power minus half, not half, from 0 to 4, because it is denominator, is it? Okay. Then multiply by x dx. Do you see that now? Then you can now look at what is here and then look at what is outside the power and see whether it relates as function derivative. Now if you look at the derivative of this, it's 2x, isn't it? But you have 2x outside, which means the part of the derivative is there, but it's in deficiency. What is it lacking? What's that? A 2. So to do that, then we must think of inserting a 1, which is a 2 over 2, and they split this one into two parts, which is 1/2 multiplied by 2. Are we making sense there? Yes? So we can put this here, 2 over 2. But once I've done that, I have now 2x as the derivative of that, but I've got half, which is redundant and integral sign. So what I'm going to do, you filter out that half, isn't it? So what can you write now? In the next line, you can write half for that half, isn't it? Then integral from 0 to 4, 9 plus x squared brackets power minus half 2x dx. Now when I'm looking at this and looking at that, I can see exactly something similar, or exactly the same type of a structure, or whatever I want to call it. There is a function elevated to power n, and that. And we know how we can get to that. The integral, the power rule of integration. Then we just apply the power rule. The power here is not -1, so the power rule can be applied. So we get to 1/2. This comes as 9 plus x squared. N, our n, which is -1/2, plus 1 over -1/2 plus 1. Then we draw our line, then say from 0 to 4. Is that making sense? Okay. Then what it follows now, we must evaluate this integral. What did we say before? We said if we've gotten a function evaluated from a to b, f of x dx, we've got to search for a function which differentiates to that. Now we've got to search for another function. Let's denote it f, capital letter F of x, which when we differentiate this function, it will give us f of x. Altogether. So once we have found that function, capital letter f of x is the one we put it here without it being differentiated, just the function which when differentiated comes to that. Altogether. Then once we've done that, we try to stroke the a, that, then we evaluate that as a f at b minus f at a, and that will give you a numerical value. Is that right? I'm reminding what I taught you, or what I said in the lectures. That will give you a numerical value. What does that numerical represent? The value represent? We say that numerical value represents the area underneath the curve from a point A to B, underneath the curve, between the curve of the function and the horizontal axis x, and that is y, and this is the curve of f of x, and the derivative of this capital letter f of x is f of x. Altogether. So then that's what we should do there now. I think you can do that now. Can you do it? So please go ahead. Right, let's continue with our simplification and evaluation of this function. I think the easiest thing to do is simplify the powers. Then the power there, then this denominator here. Simplify it to something before you evaluate. I think that's the easiest thing to do. So what we have there, we're going to have 9 plus x squared to the power half. In the denominator here, we're going to have 1 over 2. And then there we've got that constant multiplying, which is 1 over 2. And then we're still evaluating this from 0 to 4. Do you agree? Okay. So now, if we invert this and multiply here, we're going to get 1. Is that right? You see that? Okay. Because at the end of the day, this is going to look like 1 over 2 multiplied by 2 over 1. Because that 1 over 2 is dividing. Then we've got here square root of x squared plus 9 from 0 to 4. Right, check my friend, check. You see, if you are reading from here, going up to there, you can follow what this person is doing. Is it? Can you? So that's what you should do. You should write a solution which can be read by the person who is marking. So now after this simplifies to 1. Then we get this one as 16, square root of 16 plus 9. Square root of 16 plus 9 is 25, isn't it? Square root of 25 minus square root of 9, because x is 0 at the bottom, minus square root of 9. Then this gives us 5 minus 3, which is a 2 unit squared. Then we're done. But it's not easily acceptable for somebody to just move from here without showing any working, and it just lands there. That is not. You must convince what are you using. For example, after doing this here and looking at that there, anyone can be convinced that this person is using power rule, and then that's where you're going to get your part marks. But if you just get to the answer there, it might be correct, but what about the gaps we might need to fill between the starting point and the end point? Yeah. So guys, what do you think about that? Is it clear? It's fine. Okay. All right. Yes? Here, where? What do you want to talk about? I don't know which one is the first step. Can't you read the step? Read the, no. This one. Yeah. What's wrong with it?
I just don't get it. The way you move
from here to there. Then you don't know this. You don't know this. We said if you are integrating, when we're doing indefinite integral, so if you are integrating something like this with an fx prime dx, this will always integrate to f of x n plus 1 over n plus 1 plus c. In indefinite integral, that's integrated to. But now we're doing definite integral, we don't get that. I think what you are telling me, actually, what you are trying to announce to me, is that you haven't gone back to the lecture and look at what you did, and look at the video clips, or look at the notes which you wrote. That's what you're tell me. My reaction to that is that you are doing bad. You must go back and revisit what you did in class. All together? Okay, I would think we stop there for that exercise, and thank you for listening.